Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to discuss about the module Structure of Ceramics Part 2, which will include planes, directions and packing, and this is from the paper Ceramics. So after completing this module, you shall be able to understand the Miller indices of plane and direction in crystals, grain boundaries and how atoms pack in solids. And moreover, you will be able to understand how interstices are located in solid. So before moving towards, we will discuss why we need to study the structure of ceramics. As we know that a ceramic has traditionally been defined as an inorganic, non-metallic solid which is prepared from powdered materials and is fabricated into products through the application of heat. Most ceramics are made up of two or more elements and this is called compound. For example, alumina, that is Al2O3, and it is a compound made up of aluminium atoms and oxygen atoms. So the two most common chemical bonds for ceramic materials are covalent and ionic bonds. So these two bonds we have already discussed in the previous modules, but here we are giving just the introduction to understand where the structure of ceramics come and why do we need to study it. So the bonding of atoms together is much stronger in covalent and ionic bonding than in metals. This is why ceramic generally have the following properties like high hardness, high corrosive strength and chemical inertness. However, this strong bonding also accounts for less attractive properties for ceramics such as low ductility and low tensile strength. The absence of free electrons is responsible for making most ceramic poor conductors of electricity and heat. However, it should be noted that the crystal structure of ceramics are many and varied, and this result in a wide range of properties. So students, you can understand that there is a wide range of properties and such properties are due to different structures of ceramics. So for example, while ceramics are perceived as electrical and thermal insulators, ceramic oxides, initially based on yttrium barium copper oxide, is the basis for high temperature superconductivity. Whereas the other like diamond and silicon carbide have higher thermal conductivity than aluminium and copper. So the control of microstructure can overcome inherent stiffness to allow the production of ceramic springs and ceramic composites which have been produced with a fracture toughness about half that of steel. So also the atomic structures are often of low symmetry that gives some ceramic interesting electromechanical properties like piezoelectricity, which is used in sensors and transducers. So the structure of most ceramics varies relatively simple to very complex. So moving towards the structure of a ceramic, we should know what do you mean by structure. So before that, we will read the crystals, bases and lattice and how a structure formed using crystal and lattice. So the microstructure can be entirely glassy or glasses only, or it can be crystalline or a combination of both crystalline and amorphous. So in the later case, that is amorphous, the glassy faces usually surround by small crystals bounded them together. So the main compositional class of engineering ceramics are oxides, nitrides and carbides. So these ceramics can be studied by understanding the basis of the structures like lattice, crystals, planes and Miller indices, which we will be discussing in the following slides. So students, before moving to planes, directions and packing in structures, we should know about the basics of crystals and their crystallographic planes. So crystallographic planes are the identifications of various faces seen on the crystal. They are identified as HKL. So HKL resembles for a plane, or we can represent it in curly brackets, that is open curly bracket, HKL, close curly bracket, for identical set of planes where HKL are integers. The crystallographic plane in a crystal satisfied the following equation, which is given as h by a times x plus k by b times y plus L by C times Z is equal to 1. So here H by A, K by B and C by L are the intercepts of the planes on X, Y and Z axis, where A, B, C are the unit cell lengths and HKL are integers, and HKL are called Miller indices, and the plane is represented by HKL in curl brackets. So any negative indices in Miller indices of a plane is written with a bar on the top of that integer, for example H bar or K bar or L bar. So let us find the procedure for calculating the Miller indices. How to find the Miller indices? So the first step is find the intercepts of the plane with the crystal axis and express them as integral multiple of basis vectors. The next step will be take the reciprocals of the three integers found in step 1 and if possible reduce these to smallest set of integers, that is h, k and l. Now label the plane with HKL in the curved brackets. So let us take the example. So on the left hand side you all can see a figure, a cube, where you can see that 1, 1, 1 plane is mentioned. So in general, interplanar angle is given by cos theta is equal to h1 h2 plus k1 k2 plus l1 l2 divided by root of h1 square plus k1 square plus l1 square times root of h2 square plus k2 square plus l2 square. Similarly, the interplanar spacing is given as DHKL, which is equal to A divided by root of h square plus k square plus l square. So these two formulas, that is interplanar angle and interplanar spacing, is given in this slide only for the cubic case only. Now let us take the example how we can find the Miller indices. So you can see on the left hand side that all the faces of the cube are equivalent to each other by symmetry. But if I talk about the green plane, that is A, B, C, D. So we are representing this plane with A, B, C, D. Its intercepts will be 1, infinity, 1. Why it is 1, infinity, infinity? Because for the x-axis, the plane is intersecting the x-axis at 1, whereas it is infinity for y and z. That's why the intercepts are 1, infinity, infinity. So the first step is finding the intercept, which we have already calculated. Then the next step is the reciprocal of the intercepts. So the reciprocal of intercepts will become 1, 0, 0. And the Miller indices will be 1 0 0 in curved bracket. So this 0 represents that the plane is parallel to the corresponding axis. Now let us take another example which is highlighted in red color, that is OCBE plane. So OCBE plane, the intercepts are 1, -1 and infinity. So its reciprocal will be 1 -1 0. Now the Miller indices will become 1 1 bar 0 in curved bracket. Let me recall that in the previous slide it was mentioned that when the reciprocals or intercepts are negative, we are representing by H bar, K bar or L bar. So similarly, in this Miller indices, it will form like 1 1 bar 0. So the bar represent a negative intercepts. Now you can see on the right side of the figure, the yellow plane, that is the front, and the back faces which are parallel to each other are 1 0 0 plane. The purple color, that is left and right faces, are 0 1 0 plane, and the green color corresponding to top and bottom faces have the Miller indices as 0 0 1. Now let me recall that curl bracket of 1 0 0 is equal to, or it is equivalent to 1 0 0, 0 1 0 or 0 0 1. Now let us assume another plane in three-dimensional space with intercepts not equal to 1. So you can see in the figure on the top that the unit cell parameters which are cutting x, y and z axis are 4a, 8a and 3a. So the fractional intercepts will become 4a by 4a, 6a by 8a and 3a by 3a. The reciprocal of fractional intercepts will become 2, 4 by 3 and 1, and the corresponding Miller indices or the smallest set of integers will be 6, 4, 3. Now moving towards the crystal directions, let us discuss about it. So the crystal directions are basically atomic directions in the crystal. The Miller indices are, which we have discussed, which are the reciprocals of the intercepts are u, v, w. Let we are representing with u, v and w here. For a direction or for identical set of directions where u, v, w are integers. So the vector components of the direction resolved along each of the crystal axes reduced to smallest set of integers. So you can see on the left hand side, the figure shows a cube with the direction of 1 1 1 plane. So how to locate this direction? Let us take the example. So in case of 2 3 1, the direction would be 1 by 3 intercept on a cell length, 1 by 2 intercept of cell B length and 1 by 6 intercept on cell C length. So the directions are always denoted with UVW in square bracket with square brackets, and finally the direction in the form of triangular brackets with UVW. So now comes packing of atoms in metals. So in solid, we consider atoms as hard incompressible spheres which can be packed in various forms in solids. So first we will see how atoms pack in metals. Atoms in many metals form closed packed structures either in form of hexagonal closed packed structures or face-centered cubic structures. So face-centered cubic structures are where the atoms occupy the faces of the unit cells. So some metals are little loosely packed in the form of body-centered cubic structure. So in this case, in the body-centered cubic structure, the atoms are at the corners of unit cell and at the body center, that is the center point of the unit cell. So very rarely atoms pack in metals in the form of simple cubic structure. Now students, you have the basic understanding of packing of atoms in metals which we have discussed in previous slides. Now we are discussing with simple cubic structure. So the simplest structure which exists crystallographically, but in the whole of periodic table, only polonium possesses this structure. Structure contains only one atom per unit cell, which you can see in the figure on the right hand side. There is only one atom per unit cell. So, one of the important parameter of interest is the packing factor. So, packing factor determines how loosely or densely a structure is packed by atoms, and the packing factor can be represented as, or it can be calculated by taking the ratio of volume of all atoms in one unit cell to the volume of one unit cell. So, if R is the atomic radii in these structures, then packing factor for simple cubic structure is given as volume of all atoms in one unit cell, that is 1 into 4 by 3 pi r cube, divided by volume of one unit cell, that is 4r whole cube, which comes out to be 0.52. Now the next category is body-centered cubic or BCC structure. Many metals like tungsten, iron, which are present in room temperature form, possess BCC structure. So the BCC structure means that it contains two atoms per unit cell, which can be seen on the right hand side of the figure. So you all must be confused how two atoms are present per unit cell. So let us analyze this figure. So in the diagonal element, you can see that there are three atoms. So if we take center to center distance, the two atoms are forming a unit cell. Thereby, we are saying that it contains two atoms per unit cell. As similar to simple cubic structure, the packing factor of BCC structure as similar to simple cubic is given by the same formula, that is volume of all atoms in one unit cell to the ratio of volume of one unit cell. So in this case, the volume of all atoms in one unit cell will be twice into 4 by 3 pi r cube. Here why twice? Because there are two atoms per unit cell, divided by the volume of one unit cell, which is 4 by root 3 r whole cube. So the packing factor comes out to be 0.68. So in comparison with simple cubic structure, the packing factor of BCC is slightly higher than simple cubic structure. Now discussing the close packing of equal hard spheres in three-dimensional packing. So students, you can see that in a close packing, two possibilities are there. Either it can be hexagonal close pack, that is HCP, and the second is cubic close pack, that is CCB. So you can see from the animation that initially there is a single layer of atoms which are arranged together having some voids. So the alphabet A is written on each atom to signify that this is layer A or the first layer. Now the next is the voids which are present. So basically there are two types of voids which are present. So first type we have labeled with B and the second type we have labeled with C. Now The possibility of arranging the atoms in the second layer may be it covers the voids B or it covers the void C. So, there is no difference between the filling of atoms on void B or either on void C. After forming the second layer B, the third layer A or C can also be formed by putting the atoms over C. So, this is closed packed crystal with two possibilities. If the possibility is AB, then it is hexagonal closed packed, and if it is ABC, then it is cubic closed packed. Here, A, B, C layers are closed packed planes where 111 plane in FCC and 0001 plane in HCP, and the directions along which atoms touch are closed packed directions. So students, you can see the images and figure of CCP, that is cubic closed packing, and HCP, that is hexagonal closed packing figures, where you can see the arrangement in three-dimensional. So in case of cubic closed packing, three different layers overlapping one on the another is formed, that is ABC, whereas in case of hexagonal closed packing, a arrangement of two layers are formed, that is AB. So it is also represented in the unit cell form. For example, for the HCP, that is hexagonal closed packing, you can see that in the unit vector or in a unit cell, the atoms are arranged in a form of two layers. So the green layer correspond to A sites and blue correspond to B sites. Now, let us discuss atomic packing factor for FCC structure, that is face center cubic structure. Here, we are resembling atomic packing factor with APF. So, APF for FCC structure is 0.74. So, students, let's see how this 0.74 is there for FCC structure. For closed packed directions, the length is given as 4r, which is equivalent to root 2a. The unit cell contains 4 atoms per unit cell. This 4 atoms per unit cell comes out by utilizing the formula, that is 6 of 1 by 2 plus 8 of 1 by 8. So, the atomic packing factor, which is APF, is given as the volume of all atoms in one unit cell divided by volume of one unit cell. So, in the present case, it is 4 times 4 by 3 pi r cube. Here, why we are multiplying by 4? Because it has 4 atoms per unit cell. Moreover, here 4 by 3 pi r cube. Here r is the radius or length, which comes out to be root 2a by 4. So the numerator becomes 4 times of 4 by 3 pi root 2a by 4 whole cube divided by a cube is the volume of unit cell. So students, by doing such calculation, we get the value of APF for the FCC structure to be 0.74. Now comes interstices. Since the unit cell is not completely packed as packing efficiently in above structures which we have discussed is less than 100%, then there are empty spaces inside which are called interstices. These interstices are very useful because they can contain smaller atoms which modify the properties of material tremendously, such as carbon in iron makes steel and makes iron stronger. interstices in FCC structure can be of two types. So there are two possibilities. First is tetrahedral interstices, which has two per atoms. The second is octahedral interstices, which has one per atom. So in the figure which is shown below, you can see that two types of interstices can be possible and exist. First is octahedral and second is tetrahedral. For octahedral interstices, the structure which is formed or the voids which are formed is between layer A and B. So for tetrahedra interstices, it has fourfold coordinates and the sites in FCC are given as 1 by 4, 1 by 4 and 1 by 4. Whereas in case of octahedra interstices, it has sixfold coordination and it has two sites in FCC, that is 1 by 2, 1 by 2, 1 by 2 and 1 by 2, 0 and 0. So in this module, students, we have learned that planes and directions are very much necessary for the identification of various faces and directions. Atoms typically are packed in close packed manners, forming FCC, that is face-centered cubic, and HCP, that is hexagonal cubic structures, although at times they also pack in BCC, that is body-centered cubic, and SC, that is simple cubic forms too. Moreover, we have studied that the voids in the structure are called interstices, which play very important role in hosting other atoms. So in summary, if I talk about, we have learned what are lattices, what are Miller indices, how we can find the direction of a unit cell, of a plane and a structure, and what are interstices and voids in a structure. Thank you.